Good morning. We're going to be looking at the binary tree traversals today. This is Cody Henriksen. We're talking about the data structure and algorithm class for CS 2420. So when we're looking at data in a tree, we have to actually look at the entire structure itself as well as the actual nodes themselves. And when we're looking at node, we can see that we have three different ways we can look at the tree. We have the root pointer, the child pointer for left, and the child pointer for right. There are different directions we can actually look through that tree structure. The way we look at the tree, we can have to have an evaluation of which pointer we're going to go to first, aka how we're going to examine the tree structure itself. When we're talking about math, looking at different things, we have what's called permutations, and the permutations is the abbreviation for P in math. And so the permutations of 3 out of 3 means we have 3 factorial divided by 0 factorial, which is 6. Lots of different ways, but we don't care about all of them. In fact, we only care about 3 of them. We only care about the position of root in comparison to the other two values. So we have our left, root, right for our Inorder Traversal, our root, left, right for our Preorder Traversal, and finally, our left, right, root for our Postorder Traversal. And again, it's the way do I look at the different nodes to look at the other values within the tree. When we're doing a traversal, we have our default traversals which have no parameters, and those happen for the tree itself from root. So whenever I call the basic traversal of Inorder, Preorder, or Postorder Traversal, I'm automatically starting and going through the entire tree. However, I could actually do a traversal of just part of the tree at any time internally because those methods are protected methods to the class, and so I can always look inside that. Now, when we're looking at the traversals themselves, because we're using a recursive data structure, we have that implicit stack. The call structure we're using holds the information in the right order because I put it on the stack, I put it on the stack, I put it on the stack, I put it on the stack. And every time I put those values in the stack, I'm able to have that ready for me to complete. When I get done, I'm ready to move on. And so that keeps the order automatically ready for it. Now I can, like I said, do more than just the actual whole tree itself by passing that subtree value to the helper method. But when we're looking at this, we are almost always just going to be using the entire class to go through this. Now, in our examples in class, and we're looking at, if you're following along with me on my Google site, when we're doing this, we're working to the structure, we're only just outputting the data to this console. However, if you want to actually use that data from the traversal, it's a really, really hard transition. All you have to do is go to your class declaration section, add a data member, in this case list of type my data, and in the traversal itself, instead of the cout current data, you just have to change that line to be mydata.add, passing the current node subdata. By retrieving that value out of the actual node, I can simply build a list in order or in whatever order I'm actually working with. And so it's not a big change, but you can actually get that data right out of it and then have access to that data member as another method in your class. So they're Inorder Traversal. As you can see right here, we're going to go left, root, then right. And this is the main way of actually doing the information for the screen. As you can see right here, we'll just print out the information in order. So alphabetic order if we're talking about strings, numeric order if we're talking about numbers, and then the comparison order if you're talking about any other object type. So if you're looking at crime data, the least crime to the most crime is the default value. And that allows you to export it in any basic way. When we're talking about a Preorder Traversal, we're going to go visit the root first and then go look at the kiddos. And when we look at the kiddos after the root, we have a couple different things this is going to be used for. The main one of this is used for is actually in your computer is to parse out the algebraic expressions, aka math work, that your computer is doing. The Lisp language explicitly uses a preorder traversal tree to handle the idea of we're going to do the math of that. Now, preorder math is also called Polish notation or prefix notation. We see an example of that right here with plus in 742, which gives us the answer of 49. I first get the operand and the operator, and then the associated operands following it. And this can be as complex as you need it to be. And again, Lisp is a language that explicitly uses this. Many other compilers and languages use this as well to handle their math operations in a very efficient fashion. The other thing you can use a preorder traversal for is copying the tree because, oh, I've got the parent, I've got the kids, and I recursively call that down. I can build an exact copy of the tree, as you can see over here on the screen, where I have a binary search tree of type called copy. I'm going to call copy me the recursive helper method, passing it the reference to the current tree and the root itself, and return that copy when I'm done. The copy me parameter just goes back through, checks to see if it's not null pointer, grabs the node, then copies the left, copies the right, and repeats the process ad infinitum. Easy peasy chicken squeezy. We're good to go. Our Postorder Traversal is not going backwards. That's the most common misconception when we're talking about a tree. If you want to go backwards, it's actually right, root, left. You'd write a backwards traversal for that. Same basic approach, but we don't actually use them very often. If you're going to actually use that sorted data, you just take that list or whatever you're using for sort information, and then do a reverse on that to go through it in backwards fashion. However, the main use of a Postorder Traversal is destruction. As you can see right here in our destructor call, I'm going to call destroy tree my Postorder Traversal method that goes through passing it the root, and as long as the node to delete is not null pointer, I'm going to destroy its left child. then it destroys right child, and then I'll delete the node. And my tree's gone. Okay, so we have our traversals. Our in-order traversal puts the information in order. Our pre-order traversal is great for copying trees and doing math. And of course, last and definitely not least, we destroy our trees using a post-order traversal. Thanks, and have a great day.